Okay, so in this session we'll be discussing about the closed loop buck converter. Okay, in the last section or maybe last lecture we discussed about the buck converter open loop. So actually here I have to make it as a closed loop, and also I want to convert from 72 volts to 12 volt. Okay, that's my agenda. So based upon that, I gave my input 72, and based upon that, I have the values of uh, inductor, capacitors, everything. Right. So my DC voltage source will have a variation from 60 volt to 72 volt to 90 volt. Okay. So that means even I am giving 72 volt, I will have certain variation from 60 to 90 volt. Right. That's what I want. Clear. So even if it is 60 volt, I should get 12 volt. Even it is 90 volt, I should get 12 volt. That's what is the agenda of the project, or you can say closed loop. So what we have to do for that, we have to take PID part. That means the PID controller. Okay. So how to do that? Let's take this output. Let's take a constant block. Okay. Constant block will be my set point. What I want, 12 volt. Press that block, control I to reverse. Why? Because I'm moving from right to left. Select that, name as a reference point. Reference voltage. Use the some signal to get the error. Error means what you want and what you are getting. Click plus minus. Apply. Okay. Select that. Press control I. 12 to positive. This to output. This is my output. This is my output. Output. Both. Some block. This is the error. Error means reference minus what you are getting. Error. Error has to go to PID. Take PID block directly. PID controller. Okay. Moving from right to left. So I have to turn the arrow towards the input. Let's the block come. It's the PID. Select that. Left side is input. Select the block. Press controller. See. Perfect. This is my tuned output, right? This is my tuned output. This tuned output I can't give actually to the gate pulse. Okay. So I have to make the pulses. We discussed in one session, pulses means like this. We have to make the signal. Either I can give this directly by the pulse generator, or I can create with the intersection of the two wave. So what is my two wave intersection method? One wave, this is PID wave. This is wave number 1. Second wave will be my triangle wave. Okay. To take a triangle wave, take a repeating sequence. Okay, repeating sequence block will create a triangle wave. You have to give the input. So what frequency I am using? The frequency is 100 kilohertz. What is the frequency? 100 kilohertz. So based upon 100 kilohertz, we can have to set the values. So time is the reciprocal of the frequency. So here you can fix the time. Okay. So let's say here 0, right, space 0.123, 455 0.812341. What is the output? 0.1, 5.1, 0.1. Right. So how I decided, because I am taking the frequency as 100 kilohertz. So if my frequency is 100 kilohertz, that means my time value will be 1 e to the power minus 5. That will be the maximum. Half of the maximum will be mid. So I will be getting the triangle wave. I will show you the waveform also, not to worry. This triangle wave has to intersect with the PID. This is my second wave. To generate the pulse, we should go for the intersection method. Okay. So relational operator, right? Clear. The first one is triangle wave. Second one is repeating sequence. Sorry, tuned output. Resulting will give me a wave that has to go to the frequency. Connect a scope to see repeating sequence, how it looks like. You can connect a scope to see the pulses that is here. First run and see I am getting 12 volt or not. Okay, so see it is increasing and I will be getting 12 volt. Basically I haven't given the values of Kp and Pi. Just double click on the PID block and you can set the values. So proportional gain and integral gain values, we have a PID tuning concept, but as of now I am keeping 12 as a proportional gain, sorry, 0.5 as a proportional gain. Integral gain I am going for 100. I'm sorry, 0.5. Right, you can see it is approaching 12. Main thing is that if you change the voltage, it is 72 volt. Even if I change it 60 volt, I am getting the same 12 volt. Can you see that thing on the screen? Yes. Even if you change it to 90, I am getting 12 volt only. That's what is actually the requirement. So if I am changing my input, the output is still 12 volt. That is the meaning of the closed loop system. That is the closed loop control system. Okay. So it's a closed loop buck converter. Okay, where I convert it from 72 volt to 12 volt. Okay, and changing the input, still I am getting 12 volt. Right. Yeah, the waveform you can see. If you see the repeating sequence, double click on that scope. You can see the wave, how the repeating sequence look like. Okay, you can see that waveform. See, this is the repeating sequence what I generated. Okay, here repeating sequence. Okay, so also you can see the waveform, that is the pulses waveform. How the pulse is there, you can see here. Okay, see. It is a beautiful pulse. If you just zoom, you can see the pulses are how it is. It's a good pulse, correct? No? See, this pulse only I was talking that you can generate by the pulse generator, or you have to intersect the two waves. One wave is repeating, and one wave is what? PID output. Okay, right. This is the way how to do. If you are getting a notch and that thing, okay, what you can do, see, it's not proper repeating. So one setting that you can do here for the electronic switches simulation, that is very important. Go to modeling. Go to, sorry. Go to, yes. Go to modeling. Go to model settings. Okay, and change the solver to OD45 pins. It's the good solver for the power electronic simulation. Just change to here. Just change the solver configuration to OD45. Dormant pins. Press. Okay. Now run it. See the repeating sequence. It should be a perfect triangle. See, see, it's a perfect triangle. Can you see here? Right. My pulses will be the normal pulses only. See, one is off and zero is on. So this way you can go for the closed loop system. Okay, we'll be discussing in detail also. Okay, about the basics of the power electronics. Okay, if you want some, I mean to say, little bit more, I mean to say, proper, you can change it to 1 e power minus 6 actually. Discrete is good for the simulation of the power electronic segment. Okay, anyway the output will not change, it's just a way of simulation. See, you can see the repeating sequence. Okay, right, nothing will change. See the repeating sequence, it is becoming good, right? Now it is proper repeating sequence, if you can see. Right, so because of discrete, see, so let's remember the two setting. One is the 1 e to the power minus 6, and second one in the modeling setting, change to pins. So that pins will be a proper setting for the simulation of the power electronic switches. Right. See, it's a beautiful waveform of triangle. See the time period. This is intersecting with the tuned output. And if you want to see both together, so what you do, you can connect one mux block. Let's take one mux block. First stop the simulation. Basically, take one mux block. Right. Mux is multiple input, one output. So what I'm trying to tell, if you want to see the intersection, so give one input to the repeating, one input to the PID. This is in one graph, so it merged two signal. Correct? No. This is the repeating. This is the PID. So it merged. You can right click and you can see highlight signal to source. You can see here. Right. This is the repeating. That is triangle. And this one is my PID output. So I want to see both in the one graph. What will happen? You can understand the intersection part. Right. Clear. And we will take one scope. Okay. We will double click on scope and change the number of go to that gear symbol, change the configuration property, number of ports change to 2, and let's say first one is the combined, that is the combination of the repeating and the PID, and second one connect to the pulses. Okay, that is the intersection, after intersection, correct now. But this the lower graph, this one is basically, if you can see carefully, just watch videos 2 or 3 times, understand this is my gate, that is the pulses that is generated, pulses. And this one, the bottom one, is the combination, that means it is having the triangle. Such a way I'm writing vehicle so that you can identified. This is triangle plus that PID. So both are intersecting, right? Triangle and PID are intersecting, correct? No. So if both are intersecting, both are intersecting. So in one graph, that is a top plot, I can see both intersecting, and during the intersection only you are getting the pulses. So in the bottom I can see the pulses also. Okay, so that is the benefit for us. If you run it, you can understand. Okay, it is very beautiful. Let's go and check. See, so since I have two plotting, so go to view, go to layout, change the number of select the two boxes, and you can see here. See, see the intersection. See, right, the intersection of the PID output with the triangle. See, you can see clearly. So wherever there is an intersection, we have the wave. Simple. See, at the intersection of this and this, we have the off condition, on condition. So observe the top graph and the bottom graph and see the output. This is a way how to model. This blue color is the PID output. So PID is forced to intersect with the yellow color triangle to get the pulses. This is the way how to generate the pulses. Okay, so if you change the output to 60 volt or 72 volt or 90 volt, whatever, your output won't change. Correct? So perfect model to count as a project. You can build from scratch. Any output you can ping. Okay.